So at this point we've discussed displacement, velocity, acceleration, the nature of vectors, and how those vectors behave in two-dimensional motion. Now when we talked about two-dimensional motion, we talked about a parabolic trajectory of an object that was essentially given an x velocity and experienced an acceleration in the y direction. That acceleration in the y direction was invariably, for most cases that we looked at, gravity. So we really want to look at the laws that control forces and where gravity actually comes from and how we can use it. So let's take a look at the laws that govern that, which are Newton's laws. There is a story, of course, about Newton sitting under the tree and the fact that the apple hits Newton on the head, and then he basically comes up with the idea of gravity. This story is basically believed to be apocryphal, as in it didn't actually exist, and may actually have been an oversimplification to explain the effects of gravity to people who really didn't have a lot of schooling in the day and age that Newton's laws were published. Consequently, we're going to hit Newton here with an apple. Apart from in my version, lurking in the tree is also an anvil. As we'll learn later, Newton kind of deserves some of this treatment. And finally, there's a piano. All of these things would fall based on the attraction of gravity and the law of gravity between two separate masses. So today we're going to cover Newton's laws, as we said, how this affects forces, velocity, and acceleration, and the effects of gravity. As you'll recall from previous lectures, acceleration in physics is essentially a change in velocity, delta v, over time, delta v by delta t. That gives us units of acceleration in meters per second, or in terms of the integer, ms to the negative 2. There is, of course, no deceleration in terms of our terminology. That doesn't mean I won't occasionally say deceleration myself, or won't accept you saying deceleration in a civil sense, but we will simply be looking at positive or negative accelerations as results of our calculations. So if a question says there will be an acceleration, you could see your object slowing down. And of course, a negative acceleration by these terms is when our initial velocity actually is exceeded by our final velocity. So our final velocity is smaller than our initial velocity. I wanted to make sure I got that the right way around. And of course, as per everything else we've looked at so far in our kinematic journey, the equations of motion always apply. These four equations, remember the numbers don't mean anything, no order of precedence, just these are the equations. The equations of motion that we've used all the way through and how to select them is still a very important discipline in terms of V, I, V, F, A and S, and of course T. So when we deal with forces, we've already discussed briefly Newton's law of F equals ma, but here we're going to get into it a lot deeper. But force is equal to a mass times an acceleration. What happens if you have a momentum? A momentum being a mass times a velocity. Well, in the case of momenta, what we're really saying with this is for a net force, it will change momentum. A force, remember, has to be subject to an acceleration. That means a delta v. But if we apply a simple constant velocity to a mass, we will have the quantity of momenta, P equals mv. So this really shows that the impetus for an object to move under velocity. And this is that simple rule that if you're sitting at a stoplight and someone's going to hit you, you'd rather be hit by a scooter than hit by a truck, even though both of them might be traveling at the same velocity, say 12 meters per second. The truck will have a lot more momentum and do a lot more damage. Its impetus to keep moving will be much greater than that of, say, a scooter at just a few kilograms. And this is to bear in mind when looking at calculations and making sure you don't misquote a force, F equals ma, as a momentum, P equals mv. So in terms of our explorations of gravity, please remember that if we're dealing with gravity, we're dealing with a force between two masses. One of those is usually the Earth, which is very, very big. And of course, if we were to throw, say, a safe off a roof, we're looking at that acceleration due to gravity being about 9.8 meters per second. Here, rounded a bit to 10 meters per second. So after 1 second of fall time, this safe will have a velocity of about 10 meters per second. After 2 seconds, 20 meters per second. And of course, at the end of its travel, its velocity would be, of course, 0 as it hits the floor. But we'd usually look at the velocity right before it hit the floor, which if it was 3 seconds would of course be nearly 30 meters per second. So we'll restrict ourselves to talking about the Earth, on which all falling objects accelerate at about 9.8 meters per second. We're not going to talk about air resistance. We discussed air resistance and its effects in the previous section, and of course these could be added on at any particular point. So on Earth, our g is about 9.8 meters per second, and that'll increase our speed each second that our object is falling, irrespective of its mass, of course. And this is a slide we've seen before. And this was the Galileo experiment, or the experiment that Galileo suggested here, that you could take two masses, m1 and m2, where m2 is much bigger than m1 if we looked at it in terms of pounds or kilograms. You could take both of these objects and throw them off the top of a tower at the same time. If we neglect air resistance, of course, these two objects, well, even with air resistance, if they're the same shape, these two objects should hit the ground at the same time. Remember when you're doing calculations, don't get mixed up and make a statement that you wouldn't make in everyday life. These two objects, irrespective of mass, will both fall at 9.8 meters per second, gaining that amount of speed every second. And this is true on every planet you could go to. On Earth, we see an acceleration due to gravity of the typical 9.8 that we just discussed. But if you go to another planet, go to the Moon, go to Mars, go to Venus, any of those planets will also have an acceleration due to gravity. But given that those planets have lower masses, you will end up with a lower acceleration due to gravity. The effects are very much the same, but the lower mass of those planets means gravity is lower and will not have a value of 9.8. It's about 1/6 if you go to the Moon, and if you go to Venus it's about 92–93% of that on the Earth, very close to the Earth's gravity. And this was an experiment that Dave Scott on Apollo 15 performed. He looked at Galileo's experiment and took a feather and a hammer, which you can't see in this grainy 1970s image. And you can find this video on YouTube essentially, and he basically dropped the feather on the hammer and without air resistance on the Moon ended up with both of them hitting the ground at the same time. Now let's just take a step back here before we actually start dealing with the science of gravity and just think about where it actually came from. And this is a very involved story, much more involved than you might feel, and I feel it's kind of a fun story that I want to tell. The story of gravity, even though we know that Newton eventually authors the treatise on gravity, was not started by Newton. Many people had been studying the effect of gravity and knew that it existed for a very long time. However, nobody had actually quantified it. It was finally that someone such as Edmund Halley came along. Edmund Halley was one of those great scientists who did just about all of it. He was an inventor, he was an astronomer, the Astronomer Royal, a physicist, a geophysicist, a chemist, a deep-sea explorer, one of the first people to actually write down and discuss the effects of inner ear trauma due to his bathysphere experiments. He was a navigator and advisor to life insurance companies and came up with the modern theory of annuities, and eventually was a captain in the British Navy, and went out on the HMS Paramore, which was his ship, on various research endeavours. He was also what we will refer to as the Wrangler of Newton. Newton was a very difficult character, and often a loner, and did not like to collaborate with others, even though he was, by all accounts, quite a genius. And it was Halley that essentially acted as the frontman and agent for this man, and made him do his work. And it was Halley that really wanted to solve a different problem to gravity, but gravity was part and parcel of the problem he wanted to solve. What Halley wanted to do was solve the problem of comet orbits and looking at comets. Now, around Halley's lifetime was a great time for astronomers, especially those that loved to see comets. Several comets had been in the sky, very bright ones. Here's a picture of the 1680 comet over Rotterdam. And as you can see, not a lot of telescopes in use in this day. Lots of people using equipment, which is sighting devices, to try and figure out the height and length of the comet's tail and its position in the sky. And people bringing, of course, their children and their dogs down to see the wonder of the amazing comet of 1680. But people weren't sure what comets were. At this particular time in history, people thought comets were random. A single comet appears in the sky, goes away, and then eventually another comet comes and appears in the sky. No one ever stopped to think maybe it's the same comet again and again. And that's where Edmund Halley's wedding night to Mary Tulk in 1682 really kicks in. We're not sure why Edmund Halley was out observing comets on his wedding night, but he was. Now, comets don't behave in the following as shown in the following cartoon, but bear with me. So, essentially, Halley was outside, and he was observing the night sky and observing his comet, which doesn't zip across the sky like that and is there for a long time. But he looked at the comet and thought about it very deeply, as Halley often did, and thought, well, maybe this particular comet is not a random occurrence, and maybe other comets are not necessarily random occurrences either. And he thought, well, maybe just as the planet goes around the sun, maybe a comet goes around the sun in probably a much longer orbit, and maybe comets have visited us, gone back out on their orbit, and then come back again later. And this was what Halley really wanted to prove. But in order to talk about orbits in an accurate fashion, as we will later on, he had to talk about gravity and find a theory of gravity, which is a lot harder than it sounds. So in Halley's day, even though scientists pretty much accepted that comets were a very natural phenomena, a lot of people still considered them divine omens, atmospheric anomalies, or, as I said, single-time celestial events which appear in the sky and then disappear again. Halley said, well, maybe the comet orbits the sun. If so, did the same comet return in its orbit like the planets, or did it just zip off into space, never to be seen again? The comet that would eventually be called Comet Halley, or Comet 1P Halley as it's now known, has been orbiting for at least 200,000 years. It comes in close to the Sun, giving up its precious gases and volatiles as it heats up, and creating an enormous tail across the sky. The comet then comes in close on its orbit, and then goes back out into space. It gives up a lot of volatiles, gets its tail when it's close to the sun, and then as it goes away from the sun, turns back into a lifeless snowball, essentially. So it spends a lot of time out here on the edge of its orbit. When it's closer to the sun, it goes much more quickly. Consequently, comets only visit for a very short period of time, and then spend a lot of time out on the edge of their orbit. So Halley wanted to solve this. He wanted to know what would be the orbit of a comet. what would be the radius of its orbit, and how do orbits behave in general. So what Halley really wanted to do was plot this orbit, predict the return of this comet. But, as I said, we really need to know, how does gravity really affect a comet? And so, Halley talked to one of the foremost scientists of the day, Robert Hooke, and Robert Hooke was a proponent of a 1 over r squared theory of gravity. Again, Robert Hooke is another extremely talented man, and he did just about everything. He was an architect, invented microscopes, he made a universal joint, he came up with a prototype respirator, which I think we can probably thank him for in this day and age. He was a biologist and came up with a lot of microscope slides and a lot of microscope work of very small creatures. Chemist, looked at theory of combustion, was the first to see that Jupiter's red spot looked like, and rebuilt London after the fire of London. He was also a physicist and looked at the physics of gases, and as we'll see later, Hooke's law involving the force that you get from a spring when you stretch it out. Also, he was a meteorologist, geologist, and paleontologist, so this is a man that did it all. And unfortunately, there's no picture of this man left. Here is his signature, Robert Hooke, but there's no picture. Occasionally you might see, even in older slides of mine, a picture of Hooke. Turns out that this is actually a Benedictine monk that nobody knew, as opposed to Hooke himself. So there's no picture of him surviving. The reason being that Hooke and Newton hated one another. Hooke eventually died, Newton outlived him, and Newton, being a powerful man, had all of Hooke's paintings taken down from the Royal Society, taken outside onto the grass and burned. That's how much these two disliked one another. But, as I said, Robert Hooke was really a proponent of the 1 over r squared theory of gravity, and what this meant was that the force of gravity was really inversely proportional to the square of its distance from its source, or gravity fell off as 1 over r squared, meaning double your distance from a planet and its gravity would drop by 1/4. This would be 1 over 2, 1 over 2 squared would give you 1/4. And this is the kind of thing we're talking about. Here's the planet Earth, here's Isaac Newton sitting on the planet Earth now. If we calculate his weight, then we can say, when we talk about weight, by the way, we're not talking about something in kilograms or something in pounds as you would get from a scale. What that is an apparent weight. That is actually the force of gravity acting on your mass and giving you a force that's registered on a scale. So here we're literally talking about his weight as a force, F equals ma, or F equals mg. So his weight is going to be quoted in newtons here as an actual force. So the force of gravity acting on Newton, not to scale of course, because Newton here would be more than Godzilla sized, but the force of gravity acting on Newton here is 623 newtons over 1 squared, as he's sitting at the radius of the Earth, 1 RE in our abbreviation. Now take Newton out to 2 Earth radii, and you'll see that his weight now is 623 newtons over 2 squared, giving us 155.8 newtons. Take him out even further now, take him out to 3 Earth radii, and we're looking at 623 over 3 squared, so his weight is now 69.2 newtons. Let's go even further. Let's take him out to 4 Earth radii, where he's now 623 over RE squared, so over 4 squared now at 4 Earth radii, and he's going to end up with a weight of 38.94 newtons. So 1 over r squared would give you an inverse square law showing the force of gravity dropping off in this kind of fashion. Now this was well known and people had this figured out, but there was a problem. You can't just do this calculation using 1 over r squared. There's a bit of a key point missing, and that's something called the gravitational constant. And this was the dilemma with Halley and Hooke working together. So what they really needed to do was come up with this constant that made the numbers work, the universal gravitational constant. And this is the thing that Halley and Hooke couldn't quite nail down. So Hooke knew that gravity was 1 over r squared, and Halley said, go on then, prove it. And Hooke kind of tried. Not that he was a bad scientist, but it's a difficult job. When Hooke couldn't provide the proof, Halley called on Newton. Not many people could call on Newton. Newton was a very difficult man and didn't get along with a lot of people, but somehow Edmund Halley and Newton were very good friends. Very, very different people. Isaac Newton himself was essentially a single man living on his estate doing his science on his terms. Halley had many children, many friends, and was a very well-known man about town and in the Royal Society, and an excellent person for Newton to know to get work published. So, in terms of Isaac Newton, he is Isaac Newton in some of his earlier days, this was a very, very intelligent man, but some of his ideas were somewhat unpopular, and he would actually lecture to the wall sometimes when students didn't show up to his classes. He didn't really care. Isaac Newton also spent a lot of time at home, owing to the Black Death or Plague shutting down all of the universities in the country, which sounds kind of familiar, and I do get extremely annoyed when people say Newton did his best work during the Plague, and we should be doing our best work during this particular recent COVID epidemic. And I say to that, well, Newton didn't have a computer, didn't have modern communications, and wasn't being asked to Zoom all the time, so he had time to sit and just do his work when he could correspond with people, and that correspondence would take 6 months to come by stagecoach. But anyway, Isaac Newton, later Sir Isaac Newton, published the Principia that we're talking about here in 1687, and this outlawed the laws of motion and gravity. Again, as per most of the scientists of his day, he was involved in a number of things, something you're not really allowed to do anymore as a scientist. You're immediately railroaded as a physicist or a chemist or a biologist. Isaac Newton did it all. He looked into mathematics, he did the nature of colour and light, he did work on optics, invented one of the first reflecting telescopes, he invented a version of calculus that we'll talk about. He also dabbled in alchemy, something you often see the popular press laugh at Newton for, but most scientists of the day were working with alchemy. You're really looking at base metals like lead and gold being extremely similar, and so close on the periodic table that they couldn't understand why they couldn't turn one into the other. So this is not as ridiculous as it seems. Newton also did a whole host of dangerous experiments, quite often on himself. He would do such things as go out and stare at the sun. Please don't go out and stare at the sun, I will not be responsible for any damages. He also took things like large knitting needles, called a bodkin, and jammed it behind his eyeball, attempting to generate various colours. I'm guessing he probably generated red at least. Eventually, due to his fame, Isaac Newton became Warden of the Mint, meaning he was responsible for hunting down forgers and hanging them, and a lot of people were put to death on the say of Isaac Newton. But anyway, that's an aside. What did Newton actually do? Well, Halley asked Newton to come up with a theory of gravity, and Newton said, yeah, I've done that. And Halley said, what do you mean, you've done it? And he said, I've done it, I lost it. And Halley went, well, do you think you could do it again? Because that would be really useful. And Newton went away and said, sure, I can do that. I just have to invent a method of doing calculus. Not the method of calculus we use today, but a method of doing calculus. And this is what he came up with. Newton said, in words, every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Or, the force between two masses, m1 and m2, will be this. Fg is equal to g, which is a gravitational constant of 6.67 times 10 to the minus 11 meter cubed per kilogram per square second, times m1 times m2 over r squared, where r is the distance between the objects. This is the 1 over r squared relationship we saw previously. So this is what he came up with. You can see one key difference in here that people hadn't really applied before. We can look at m1, m2 and r squared, but what he hadn't applied before was this. And this was the true genius of Newton, and how he had to come up with this value of G, 6.67 times 10 to the minus 11 meter cubed per kilogram per square second. And this gravitational constant suddenly enabled people to do calculations involving gravity that they'd never been able to do before. And I really like this picture. Not only does it show Newton in a totally incorrect light, but he's got all of his best inventions just happen to be sitting around him while he's doing this. And Newton, to do this, had to look at various graphs and invent a version of calculus. Now, the version of calculus that Newton invented is not necessarily the version of calculus that we use in popular mathematics today in terms of the dy by dx or integral symbols. This is the notation of Leibniz, whereas sometimes in physics you can still see the y dot or x bar or y bar integrations and differentiations, but a lot more rarely than you see Leibniz notation, which was put together by Leibniz in Germany. So he invented his own version of calculus and came up with the gravitational constant of G. And of course this would eventually get published in Newton's Principia. Now, the story of Principia is kind of involved. It doesn't just get published nicely because everyone went, Newton, what a great piece of work. Halley and Newton came up with Principia, of course, Halley and Newton doing all the work, and Halley said, you should publish that, and fast, before someone else manages to get this out there. And, of course, they went to the Royal Scientific Society in London, and they said, sorry, we can't do that, even though Halley worked for the Royal Society. They said, we can't do that because we just blew the entire publishing budget for the year on De Historia Piscium by Francis Willoughby. This was particularly embarrassing, so Halley financed the publication of Principia himself. One of the big works in the whole history of science was paid for by private money because the main societies and main establishment had blown all their cash. One of the ironies of this, of course, is that Halley worked for the Royal Society and withdrew his wages from them. When they ran out of money, they simply paid him in copies of this book on fish. So he had more copies of De Historia Piscium than he knew what to do with. Eventually, the Royal Society burned most of their copies because nobody wanted to buy it. This is particularly embarrassing at the end of the day, because now a first edition of De Historia Piscium by Francis Willoughby here is actually worth more money than a first edition of Newton's works because of its rarity. Bit of historical irony for you. So again, Newton's law of gravity here, every particle in the universe attracts every other particle with a force directly proportional to the product of their masses inversely proportional to the square of the distance between them, or F is equal to g m1 m2 over r squared. And this is the calculation. And this constant here was Newton's baby. This was Newton's constant for universal gravitation that enabled the entire universe to start being observed in terms of energy and in terms of gravity, and solved so many problems. One of the things that could be done is people could look at the different planets. They could look at the orbits of moons around Jupiter and figure out the mass of Jupiter and the mass of the moons. They could revise the mass of the Sun based on the Earth's travel around it. They could start to apply other laws, such as the laws of Kepler, which had been done previously on planetary motion, and put this correction in for Newtonian physics, which truly explain the motion of these planets. You could also calculate the sizes of these other planets and, of course, the gravities that you might see at their surfaces. So we know that most planets in the solar system, in fact all the other solid planets in the solar system, actually have lower mass than that of the Earth. And as a result, that means that we can look at the surface gravities, and the surface gravity here of Mercury, even though it's an extremely dense world, Mercury is a very small planet, its gravity is at about 0.4. Here we're showing the gravity of the Earth to be 1. 1 is equal to 9.8 meters per second. So these gravities are shown in multiples of the Earth's gravity. So take each of these numbers and multiply by 9.8 to get an actual answer in meters per second per second. Here, Mercury, 0.39, small body, very dense, but not very big. Venus, almost Earth's twin in size, 91% Earth's gravity, very close, even though visiting it would be practically impossible due to the fact that if humans went there, you would be boiled and crushed by its incredibly thick 92 bar atmosphere. Earth, here we are, 1 gravity, 9.8. Mars. Now when you actually see any movie on Mars, they're nearly all wrong. They never really show the true gravity. The only movie I've found that really gets the physics of Martian gravity right is South Park, which is quite embarrassing for movies like The Martian, which sell themselves as trying to be accurate. But here, Mars, 0.38 in terms of gravity. It's a small, not very dense planet, and people look to it far too optimistically as a colony world. Jupiter. Now, I realise that these planets here from Jupiter to Neptune are actually gas giants and have as such no really discernible or reachable solid surface. These gravities are based on their mass and are gravities at the surface of their atmosphere. Jupiter, biggest planet in the solar system, 2.6, getting towards 3 times Earth gravity. Saturn, second biggest planet in the solar system, has a gravity of 1.1. Very similar to the Earth. This is because even though Saturn is a very, very big planet, its gravity is actually quite low due to the fact that its density is small. If we look at our equation, the force of gravity was gm1m2 over r squared, where r is the separation from the centre of mass of a planet. Consequently, or the body, but consequently because of this, if we look at that particular calculation, because the density of Saturn is so low, then its mass, even though it's a big planet, is also low, giving a low gravity of 1.1. Uranus and Neptune are a very similar deal, both of them rather large planets, but given 0.88 and 1.14 in terms of their gravitational attractions, due to the fact that their densities are not that high. Pluto, of course, tiny little body, not a lot of mass, 0.05 Earth gravity. So let's just talk about weight and mass for a moment and throw in this reminder. Mass is a measure of the amount of matter you have in an object, and this is measured for our purposes in this class in kilograms. You could of course measure it in pounds or other units, but here we'll use our calculation always in kilograms. So mass is the amount of matter that you have. It's not actually a weight until a force is actually implied upon it, and that means that you have to have F equals ma. M is how much mass you've got in kilograms, and weight is the force, F equals mass times G in our case. So there's a fundamental difference in terms of physics, and this is often misunderstood in questions when you're asked for a weight. If you see a weight in a physics sense, immediately go for something in newtons. If you see a mass, this is an amount of matter in kilograms. And as we saw before, the force of gravity varies on different planets. Your mass will be the same on every single planet that you visit. Your weight, however, will change based on the planet's gravitational attraction. F is gmm over r squared, the mass of the planet times your mass over r squared. So the weight will change depending on the planet's gravity. We'll talk about weightlessness here shortly, but when we talk about weightlessness, we're really talking about an object that's in free fall. Even if you're in orbit, gravity is still acting on you, and its force is not diminished that far from 9.8 for the case of Earth's orbital radius. But when we're talking about falling objects, something we said before was all objects fall at the same rate. Drop something of 10 tons or 4 kilograms, and they will fall at the same rate due to gravity. But we haven't really said why. Now, we've said this previously, that the force of gravity on Earth is gm Earth, and if we drop a ball, m ball, over r squared. So if we look at this, we can say, well, this is our force of gravity, gmm over, and let's just not worry too much about what elevation a ball is at. We can assume that even if it's at the top of a tall tower, that radius is small compared to the radius of the Earth, which is enormous. So we're going to replace r with the radius of the Earth squared. This is a force of gravity. We also know that F equals ma. Now if the acceleration of the ball is equal to the mass, the force of the ball is equal to the mass times acceleration, and it's equal to gmm over r squared, for any ball which is dropping under the action of gravity, we can make this calculation. Gmm over r squared equals ma. Ball here appears on both sides of this equation, and of course will cancel out. Because of this, we can say if our force of gravity will be gm Earth, the mass of the Earth, over r squared is equal to the acceleration of the ball. And this is why you often see the force of gravity on Earth quoted both as a force in terms of newtons and also as an acceleration interchangeably in the case of physicists. So the mass of the ball is irrelevant. The ball will fall of 2 pounds or 3 tons will fall at the same rate because of this effect.